Hello and welcome. Today, we're going to break down one of the most incredible pieces of biological engineering you could possibly imagine, the human eye. We're going to go on a little journey from its very first spark of creation all the way to the complex machine that's letting you see me right now. All right, let's get into it.
No, really, stop and think about that for a second. Light is literally traveling from your screen, hitting your eye, and then somehow getting converted into a coherent reality inside your head. It's a process that's so smooth, so seamless, we totally take it for granted. But the story of how it all happens, it's just extraordinary.
Just look at this thing. It's so much more than just an organ, right? This is our primary interface with the world, a biological marvel that lets us perceive everything from tiny text to the vastness of space. It's a sensor, a processor, and a transmitter all rolled into one beautiful, intricate package. But to really understand how this thing works, we have to go back, way back. We need to see its origin story, how it's built from practically nothing, just a few cells, into a fully functional optical instrument.
Okay, so what's really wild about this is the speed and precision of it all. In just 3 weeks, the first little sign, the optic groove, appears. By the first month, the lens pit is already forming. And get this, by month 3, the precursors to our light-detecting cells, the famous rods and cones, are already starting to differentiate. It is an absolutely astonishing pre-programmed dance of development that just keeps going even after birth.
And this is where it all begins. Believe it or not, the eye starts as just a simple little pocket, pushing out from what we call the neural ectoderm. Now that's the exact same master tissue that's going to form the brain and spinal cord. So in a very real way, the eye is literally a piece of the brain reaching out to see the world.
So this pocket doesn't just grow randomly. It's incredibly purposeful. It extends outward, forming a structure called the optic cup. You can think of it like it's on a mission, reaching for the outer layer of the embryo. And this is where the magic really happens. When that optic cup touches the surface, it basically sends out a signal, a chemical instruction that tells the surface tissue, hey, you, thicken up and form the lens. That tissue then sinks in, pinches off, and separates. It's a perfect, beautiful example of different tissues talking to each other to build something totally new.
And from those first simple folds and cellular conversations, this whole intricate process just keeps going for months. Cells multiply, they specialize, layers form, connections are made, until you have this, a nearly complete eye, a masterpiece of biological architecture, all from that simple initial blueprint.
All right, so the eye is built. Now for the fun part. Let's put it to work. We're going to follow a single particle of light, a photon, on its ridiculously fast journey from the outside world all the way to the back of the eye, where sight really begins.
This cross-section right here, this is going to be our map. Our photon's journey is basically a race through a series of incredibly specialized, totally transparent structures. And the starting line is right at the very front surface, a part called the cornea.
The cornea is the eye's protective front window. The source material has a great description for it, calling it a watch glass. It's perfectly clear, perfectly curved, and its main job is to bend the incoming light. It actually does about 2/3 of the heavy lifting when it comes to focusing the image.
But don't let that simple, clear appearance fool you. This so-called simple window is anything but. The cornea is actually made of 6 distinct, highly organized layers. Each one has a very specific job, from providing a self-healing surface on the outside to constantly pumping out water on the inside to maintain that perfect transparency. It's so complex. Okay, so once our photon makes it through the cornea, its path is controlled by the iris. This is the colored part of your eye, and it works exactly like the aperture on a camera. It expands and contracts the pupil to let in just the right amount of light, whether you're out in the bright sun or in a dimly lit room. Next up, the lens. So while the cornea did that first big, coarse focusing adjustment, the lens is all about the fine-tuning. And unlike a rigid piece of glass in a camera, this thing is alive and it's flexible. Tiny little muscles pull on it and change its shape, which is what allows you to seamlessly shift your focus from a distant mountain to the words right in front of your face.
Our photon has now blasted through the cornea, the pupil, and the lens in a fraction of a second. It's reached its final destination, the retina. This is it. This is the sensor. It's the biological film at the back of the eye. Its entire job is to take that physical particle of light and turn it into the language of the brain, an electrical signal.
And if you thought the cornea was complex, well, just look at this. The retina isn't one simple layer. It's 10 distinct layers of neurons and support cells, all stacked into a supercomputer that's barely half a millimeter thick. Layer 2, for example, that's where our light detectors are. The signal they create then gets passed down through the other layers, getting processed and refined by other neurons before it's even sent to the brain. And this just perfectly illustrates the scale of it all. On the left, you're seeing those dense layers of tissue under a microscope, and on the right, that's a drawing of one single photoreceptor cell. We've got two main types: cones for sharp color vision and bright light, and rods for detecting motion and seeing in the dark. These are the individual pixels that physically catch the photons and kick off the whole process of sight.
So we followed the path of light, but this entire system is a living, breathing organ. It needs power, it needs plumbing, and it needs a maintenance crew to keep it all working. So let's take a quick look at the unseen support crew that keeps this whole operation running smoothly.
Here's a crazy fact. Vision is incredibly energy hungry. The retina has one of the highest metabolic rates of any tissue in the entire body. That's why it needs this super dense network of arteries and veins, supplying a constant stream of oxygen and nutrients. And just as critical are the systems that manage the fluid pressures inside the eye. If that pressure gets too high, it can crush the optic nerve and lead to diseases like glaucoma. So it's this constant, high-stakes balancing act.
So as we start to wrap up this journey, it becomes really, really clear. That camera analogy we've been using, it's helpful, for sure, but it barely even scratches the surface of what the eye truly is.
This quote from our source material just nails it. The key words here are translated and transmitted. See, the eye doesn't just record an image like a camera. It actively processes information. It translates the physical world of photons into the electrical language of the brain before that signal has even left the eyeball.
And that kind of leaves us with one last big thought. We've seen the incredible mechanics of this biological camera, from how it's built in the womb to the journey of a single photon. But after the light is captured and after the signal is sent down the optic nerve, the final mystery remains. The eye delivers the data, but who or what is actually watching the film? And that's a question that takes us way beyond anatomy and deep into the nature of consciousness itself.